So we started out, number one, the most of the credit will be on just getting your rule right. So the bottom, 6x minus 5 times root of the top, 6x minus the top, 3x squared plus 7 times root of the bottom, 6 over 6x minus 5 quantity squared. You simplify this, right, you get 36x squared minus 30x minus 18x squared minus 42, all over the same thing, which simplifies to 18x squared minus 30x minus 42 over 6x minus 5 quantity squared. Okay? Now, the next one was similar. 10x squared plus 4 to the bottom times the top, 6 minus the top, 6x minus 2 times root of the bottom, 20x, all over the bottom squared, 10x squared plus 4 quantity squared. I simplify that top, I get 60x squared plus 24 minus 120x squared plus 40x, excuse me, over the bottom squared. I simplify this top, I get minus 60x squared plus 40x plus 24, all over the bottom squared. The next one was the product rule. Okay, first times the root of the second plus second times the root of the first. Now, you don't remember the rule, you're going to lose major points there. So you want to make sure that you remember those rules. Okay, so we have the first, 6x squared minus 5 quantity squared times the root of the second, 3. Now, you can do second times the root of the first like that, but because it's added, it doesn't matter. But I always do first times the root of the second, 3x minus 2 squared times the root of what's inside plus the second, 3x minus 2 quantity cubed times the root of the first, 2 times 6x squared minus 5, 12x. Okay, now if I simplify this, now this would be most of your credit right here. Now I simplify this, I'm going to pull out the highest power in parentheses. So I have 3 times 3x minus 2 squared, 6x minus 5. And what is left is 6x minus 5 plus 3x minus 2 times 8x. And then you simplify that, you get 24x squared plus 2x minus 15. You know, this right here is, like I said, is most of the credit. The rest is algebra, and this is a calculus test. The next one is, again, it's the chain rule. So I just did the chain rule, the product rule, and the chain rule together in number 3. So, for example, if I had sine x and then I had, ln x, right? That's the product rule. The first ln x times root of the second cosine x plus the second sine x times root of the first 1 over x, right? It doesn't have to have, you don't have to use the chain rule and the product rule. You can just use the product rule. But in that problem, I used both. Now we're using the chain rule and the quotient rule together. So we have the bottom 3x minus 7 times the derivative of the top, 2 times 6x to the 7th minus 5 times the derivative of what's inside, 42x to the 6th, minus the top 6x to the 7th minus 5 quantity squared times the root of the bottom 3, all over the bottom squared. If I simplify that, I'm just going to pull out this 6x to the 7th minus 5. 6x to the 7th minus 5. What do I have left then? I have 3x minus 7, 84, x to the 6th minus 6x to the 7th minus 5. One of those left times 3, all over 3x minus 7 quantity squared. I think that would be enough simplification. Okay, now the next one is, again, the product rule and the chain rule. So I'm making the product rule hard here, pretty hard, because I want you to understand both. So we have the first 5x cubed minus 1 to the 4th times the root of the second, 3 times 2x to the fourth minus 3 quantity squared times the derivative of what's inside. Okay, plus the second, 2x to the fourth minus 3 cubed times the derivative of the first, 4 times 5x cubed minus 1 to the fourth, to the third. To the third times the derivative of what's inside, which is 15x squared. All right, so this is our first step. Okay, now, what could I pull out to simplify this? Okay, I'm going to pull out this to the third power and that to the second power. So I'm pulling out 2x to the fourth minus 3 squared and 5x cubed minus 1 cubed. What does that leave me? It leaves me one of these. And I think that's enough. The last one was the chain rule and the quotient rule. Again, it's almost identical to 4, right? So you're going the bottom 6x squared, 6x plus 1 quantity squared times the root of the top 5 minus the top 5x minus 2 times the root of the bottom 2, 6x plus 1, 6 all over the bottom squared, 6x plus 1 to the fourth power. I simplify this. I'm going to pull out the 6x plus 1. So I get 6x plus 1. What do I have left? I have 1 6x plus 1 times 5 minus 5x minus 2 times 12. All of this simplify over the bottom squared still. All of this simplifies to 6x plus 1 times minus 30x plus 29 all over 6x plus 1 to the fourth. But like I keep saying, the main thing is that you get that calculus right. Okay, now let's go through your homework of 2000. Okay, so 2000, it wasn't that bad. What you needed to understand was if they give you the time for 10 cycles, you have to cut that into 1/10 of that to get your period. Your period is the time for 1 cycle. So they gave you the time for 10. So you had to get 1/10 of that. Okay. Once you get 1/10 of that, and then you plot that here. There were 4 points. Now, we're always then getting our slope and plugging that into an equation. For correctly plotting the square of the period as a function, you got 1 point. For drawing a single straight line, you got a point. For drawing this line to approximate best fit, you got a point. So what do? You look at your equation. You know your equation, what you have on your equation sheet is this. And they asked you to figure out G. Okay, so I just plotted T squared versus L. So you want to get T squared and L on one side of the equation. So I have T squared is equal to 4 pi squared L over G. Okay, so if I divide down that L, I get T squared over L is equal to 4 pi squared over G. So your slope is equal to 4 pi squared over G. You have to know how to do that. It's so common on the test. So you take the equation, you fit your slope into it by going y squared over x on one side of the equation. Everything else on the other side is the equation with the slope. Or you could have written it like this. T squared is equal to 4 pi squared over G times L, where you have y is equal to mx. This is the x, this is the y, and this is the m. You take that slope, you set it equal to this, so then G becomes 4 pi squared over the slope is equal to your G. Naomi, did you get a G?
I got 9.87.
Good. It should come out to right around 9 point something. They have 8.77, but it shouldn't be far from it. Okay, then within plus or minus 4% of the experimental value. So actually 9.77 might have been a little bit more than 4%. Oh no, they just asked you that question. Let me see. If the measurement or apparatus allows you a determination of G that is accurate within 4%, is your experimental value in agreement with the value of 9.8%? 9.8. Okay. Credit was awarded if the answer was consistent with the value. So if your value was, incorrect and you got 6 or something, and you showed that, you still got full credit. Okay, so do your percent error. You've done that so many times. They wrote it this way. Okay, one minus the other divided by this. Either way, you can divide by either one. They get their percent error, and it was more than that. So you just had to get your percent error. Then you write your sigma Fy. Someone informs you that the experimental apparatus is in fact near Earth's surface, but that the experiment has been conducted inside an elevator. We did all these elevator problems in Physics 1. Determine the magnitude and direction of the elevator's acceleration. Okay, so if they're going up, we're going to have normal minus the weight is equal to ma. If they're coming down, we flip that. But you can use either one and see whether you get a positive or negative acceleration. So they put it like this, normal minus the weight is equal to negative ma. And the normal is mg experimental. We spoke about that in Physics 1. You cancel out your mass. And so G experimental, they solve this. They get 1.03. What is your acceleration in an elevator? We talked about that. So basically, it comes out to be the difference between the two. Okay. So when you're in an elevator, if you're going up, right, you're feeling heavier. If you're going down, you're feeling lighter. The acceleration is more going down. It's less going up. Okay, then you had also the ones where you should know by now all those sigma Fy's. So the first one, they're not moving. They're equal on the two sides. You set it equal to 0. Then it's moved till you have 3 on one side. So you should change it. Tension minus 3 mg. So I would write it like this. Minus 3 mg is equal to 3m. They told you that was g over 3. T3 is equal to, this is moving down. Either way, you're going to get 2 mg. Okay. Then the other one, you just have 1, so that's easier still. Tension minus weight is equal to mg over 3, so you get 4/3 mg. For the next one, you have something that is rotating and translating. So you have your torque is I alpha. You do this step-by-step process, plugging in for getting rid of alpha with A over R. And we have this, the difference in the tensions. I've talked about how when you have 2 pulling, you have 2 different tensions. Okay. You go through the step-by-step process, writing your sigma equation, writing your torque equation, plugging in. After that last page, it got harder. You have to recognize that the tangential speed for both is V, so it's omega times R for both pulleys, omega 1, R1. They have the same tangential speed. So therefore, you can write this equation. If one has twice the radius, then omega is going to be half as much. Just subbing in for angular momentum, if you did the wrong, for correct substitutions, L equals I and omega. If you had the wrong I and the wrong omega, you subbed in, you get full credit. For writing that you have your 2 types of kinetic energy, you got a point that they're both moving, they're both rotating, and then subbing in you got for correct substitutions and solution. But if you had the wrong answers and you plug them in, you still get your point. Okay, so let's. We still have to finish both 2000 and 2004. The rotation ones are often the hardest ones. So and we haven't done two, so let's do number 2 on 2004. This is very similar to one you've done before. In fact, it's almost identical. So we're looking at the one that says a rubber ball of mass M in 2004. Anyone have it? Okay. Samuel, we're looking at number 2, 2000. This one, a rubber ball of mass M. Is that 2000 or 2004?
2000.
Yeah, it's 2000. Okay, can you read it, Violet?
A rubber ball of mass M is dropped from a cliff. As the ball falls, it is subject to air drag, which is the force caused by the air. The drag force on the ball has magnitude v squared, where v is the constant drag coefficient and v is the instantaneous speed of the ball. The drag coefficient v is directly proportional to the cross-sectional area of the ball and the density of the air, and does not depend on the mass of the ball. As the ball falls, its speed approaches a constant value called the terminal speed. A, on the figure below, draw a map of all the forces on the ball at the same instant, at some distance before it reaches terminal speed. B, state whether the magnitude of the acceleration of the ball mass m increases, decreases, or remains the same as the ball approaches terminal speed. Explain. C, write but do not solve a differential equation for the instantaneous speed v of the ball in terms of time t and the given quantities and fundamental constants. E, determine the terminal speed v in terms of the given quantities and fundamental constants. And E, determine the energy dissipated by the drag force during a fall as the ball is released at height h and reaches its terminal speed before hitting the ground in terms of given quantities and fundamental constants.
Okay, this is almost identical to another one that you did. See if you can start with labeling the forces. We did the terminal speed problem, remember? It's exactly equal to that. Think about what's happening at terminal speed. Draw and label all the forces. Don't make that harder than that is. That's not hard. How many vectors do you have to draw?
Just two.
2. What are they? Right. You have the weight and you have the drag force. Now they should be going in opposite directions, right? The weight and then the drag force. For a vector arrow pointing downward, you got a point. For a vector arrow pointing upward, you got a point. For correct force labels on both vectors, you got a point. For any extra vectors drawn, they deduct a point.
Does it matter which one you put?
Well, they told us that the drag force was supposedly. But in theory, you don't have to put in the negative at that point. They gave you the magnitude, you could just write the magnitude. As long as you're showing that it's going in the opposite direction. Okay, so when they say you have to, you have to talk about the forces acting in your justification. So you just know you're going to be talking about forces. They've just given you this force, BV squared. State whether the magnitude of the acceleration increases, decreases, or remain the same, and explain. So you have to talk about the forces acting because that's what changes acceleration. They're talking about before it reaches terminal speed here, but that's, you have to speak, in order to do the physics, you're going to have to speak of the forces. What'd you put, Connor? Increases or decreases?
Put decrease.
Right, it decreases. For putting decreases, you get a point. You get 2 points for a correct explanation that includes a correct mention of forces. Partial credit of 1 point given for only a statement including a basic definition of terminal velocity, like at terminal velocity, velocity is constant, so A must decrease. That's only 1 point. You have to talk about forces. What happens with the drag force? You know what happens at terminal velocity with their forces. Now we did the same exact thing when you get to write but do not solve the differential equation. That is the same exact question you answered before. Okay, so for example, as the ball approaches terminal speed, the velocity increases, so the drag force increases and gets closer in magnitude to the gravitational force. The resultant force, which is the difference between gravitational and drag forces, gets smaller. Since it is proportional to the acceleration decreases. Probably you didn't have to say all that, but you could say that as it speeds up, the drag force is increasing and it's getting closer to the weight. So the net force is getting smaller and the acceleration is getting smaller. Okay, now in C, you should know what you're doing. It's the same question they asked before. Now, if you don't have any idea, well, you see something and they've given you a force and it's falling in air, you know you're writing your sigma Fy at some point, and there's no other way. So just write your sigma Fy. Once you write your sigma Fy, it's the same thing that they asked before about the differential equation. You're doing the same exact thing you did last time. Right? But do not solve a differential equation for the instantaneous speed of the ball in terms of time. You did that same exact thing. Remember, you're plugging in. So your sigma Fy you know that one well. You should have written dv squared minus the weight is equal to negative ma. If you switched all your signs, that's okay. Since you switched all of them and not some of them. You know what it is? Same with the last time. I should just look at your other problem. You have a problem? It's the same exact question. No, it's only the problems. It's the same. Naomi, do you know how to write the differential equation? Connor, do you remember? Okay, just look at your old problems. find it. Samuel, what do we do? I thought you said you just found it.
I found it.
What is it?
Like our sequence fire.
What's the differential equation?
Acceleration equals dv dt.
Right. All you have is your acceleration is dv dt. A differential equation for the instantaneous speed of the ball in terms of time and fundamental constants. Okay, so you're plugging that in for A. Then you isolate your dv dt. Then they ask about terminal velocity. If that's the same exact question as last time, you do the same exact thing. Isolate that dv dt, and then go on to D.
The two negative m's, do they cancel each other?
No, because you have that bv squared doesn't have an m in it. What do you do in D to get 1 point? Violet, do you know? Something you write to get 1 point. You have to write something about terminal speed. What do you write? It's the same thing we did last time.
Acceleration equals 0.
Right. If you write acceleration equals 0, you get your point. Okay, so when you isolated your dv dt, we had to move over that negative. So I'm going to write it as mg minus bv squared over m was equal to dv dt. Okay, you should have gotten this. Then you write acceleration is 0, you plug in 0.
Put negative though.
I moved the negative over. I multiplied both sides by negative, so I switched these signs right here.
So the dv is just so that we keep it in terms we have, right?
They told us to put it in terms of this, but now we're done with that in C and we're moving on to D. And in D, you're setting your acceleration equal to 0 and isolating your V. And then in E, you're looking at your energy. That's not hard. Just write your conservation of energy for something with a drag force. Show me if you have your terminal velocity. So we set this equal to 0, we get mg minus bb squared is equal to 0, right? You move up that m and the whole right side is 0. mg is equal to bb squared, we bring down the b. Take our square root and we're done. So a drag force is work not conserved. So we get mg over b, the square root of that is equal to our terminal velocity. I'll just call it dt. All right, you know a drag force is work not conserved. So write out, you're looking at your conservation of energy equation, putting in what's happening, putting your work not conserved, and then isolate that work not conserved because that is our loss in energy. Determine the energy dissipated before hitting the ground. Okay, drop from a height h. So just write out your conservation of energy equation, put in your work not conserved, isolate that, work not conserved. Look in your packet, you don't know how to write your conservation of energy equation. We've done that so many times. Show me if you have your work not conserved. Now remember, at some point, we're always subbing in what we got earlier. You have your conservation of energy equation in your pack. You don't remember, it's page 3. Show me when you're done.
What one is it this one? This one?
It's this one right here.
Oh,
Starts here, so it's
it's this.
not conserved. That's what you're solving for. That's the drag force. So that's what you're isolating. It reaches its terminal speed before hitting the ground. And we gotta put in what these at. Remember, we're always subbing in what we got earlier. So you have to use the given quantities in They meant just before it hits the ground. It wasn't very clear. You might have thought it was some distance above the ground because it just says before hitting the ground, but they mean just before hitting the ground. Naomi, what do you have? Okay. Okay, it starts from rest, a rubber ball is dropped, so we only have potential energy when it's dropped. We have work not conserved, which is this drag force, and then just before hitting the ground, it reaches its terminal speed. Okay? We're looking for this work not conserved. That's what we're isolating. That's a drag force. Now we have to plug in for our terminal velocity that we got earlier, which was square root mg over b. So if we square that, we're going to get mg over b there. Okay, is equal to my work not conserved. All right, that's it.
Yeah, you just correct us from simplifying, but if it's m times mg over b, could you say 2 mg and then cancel the 2 with the 1/2?
There's no, if you want to simplify this, you could pull out an m. Okay, so you have gh minus m, 1m would be left. I could pull out a g also. So I pull out an m and a g, and I have h minus 1m over 2b. But you can't cancel anything unless you want to multiply everything by 2. So if you want to multiply both sides of the equation by 2, but then you have a 2 there. So that's about all you can do. Okay. We never finished 2004. It was a rotation one that I wanted to do with you, so let's go there. 2004, number 3. It's this one. Everybody have it?
Yeah, I saw it.
Do you have it, Naomi? Samuel, can you please read it?
Yes. A uniform rod of mass M and length L is attached to a pivot of negligible friction as shown above. The pivot is located at distance L over 3 from the left end of the rod. Express all masses in terms of the given quantities of unknown constants. Calculate the rotational inertia of the rod about the pivot. B, the rod is then released from the rotation or horizontal position shown above. Calculate the linear speed of the bottom end of the rod when the rod passes through the vertical. C, the rod is brought to rest in the vertical position shown above and hangs freely. It is then displaced slightly from this position. Calculate the period of oscillation of the springs.
Okay, so read that over.
The inertia. Do we have the inertia for a rod in the packet?
No, but they told you the pivot is located at a distance L over 3. Calculate the rotational inertia of the rod about the pivot. Now, they basically, the easiest way for you to do this one is to remember What is the rotational inertia of a rod about through the middle? Does anyone remember that?
Is it 1/12?
1/12 ml squared. Now that's not the answer, right? You're going to have to use the parallel axis theorem. Do you remember that? It's in your pack. It's on page 4. To get the inertia about through a parallel axis, I have it there at the top. So use what you know about a rod with the axis through the middle, and then calculate it through that point using the parallel axis theorem. Everybody find it? Okay, so you're using that. I, is I center of mass, right? That's the 1/12 ml squared.
That's 1/12 ml squared.
So I have there, h is the distance from x, to parallel axis. So you have to figure out what that is in terms of L. And then you should simplify. Show me when you're done. You want to square that entire term. And I'm looking from the axis of rotation, which is right here in the middle, to the pivot, which is right here. Sorry, Nancy, since you're sick, I'm just doing it right. So we need to know the distance from here to here. It's very obviously not L over 3. And then you have to plug that into the equation. Naomi, can you tell me what that distance is? Connor, do you know? Violet?
1/6.
Right, you're going to have, so you have L over 2 minus L over 3, or I can just go 1/2 minus 1/3. You get your common denominator, that's 3/6 minus 2/6, which is 1/6. This is L over 6. Now that's quantity squared. So you have to simplify this. Any statement of the parallel axis theorem, you got a point. For correct value of the center of mass inertia, calculated or remembered, well, you know, that should be allowed to calculate that when you have this limited time. That's why it helps to remember it. Then you get a point for putting in L over 6. But you had to, it looks like they expected you to simplify it on this one just because then you're going to be probably plugging in this in later, right? Show me when you have your simplified answer. Okay, so you square that L over 6, you get L squared over 36. So we get L is one. I'm going to pull out the ML squared for now. And I get 1/12 plus 1 over 36. My common denominator is going to be 36. So I have ML squared 3 over 36 plus 1 over 36, which gives me 4 over 36. So 4 over 36 is 1/9. So I get ML squared over 9. Okay, now, if this thing is rotating and it's dropping down, you can guess it. We're going to be, whenever you see something rotating, you should be thinking, okay, I can be using conservation of energy for something rotating. I can be using, I could consider my torque equation. Okay. So let's go to B. It's released from rest from the horizontal position as shown. Calculate the linear speed of the bottom end of the rod. So they're looking for V. When it passes through the vertical, we're only getting the speed at the bottom, that V. Okay, so this is not translating. It is only rotating. So what you're going to have to do is put it in terms of omega and then put omega in terms of V. You see something falling, it is so commonly conservation of energy. So let's say you do your conservation of energy for something that is rotating like this.
Which one were we using?
Conservation of energy.
What's the one?
What?
The same one we just used.
We just did parallel axis theorem. You mean from the last problem?
Yeah.
Well, the last problem, it wasn't rotating. I have something at the bottom of page 4 on conservation of energy, something that's rotating and translating. But this is just rotating. So see if you can modify that. Okay, so we have, for something rotating and translating, we have mgh is equal to 1/2 mv squared plus 1/2 I omega squared, but this is just translating, so we get rid of, just rotating, so we get rid of that term. Now, okay, we can't use h. We have to figure out how much this thing dropped down. So what do we care about is how much the center of the mass dropped. Because this thing drops a lot, and this point here hardly drops at all, and that drops a different amount. So what we want to know is how much has the center of mass dropped. So this is the center of mass here. This is the center of mass here. How much did the center of mass fall? That is your height. It's like when a meter stick falls, if you have a meter stick falling, we would put it as mg times 50 centimeters because the center of mass dropped 50 centimeters. So you have to put how much did the center of mass fall here, put in the I you got, Substitute, get rid of omega. You know how to get rid of omega? We're trying to solve for V, and that's in your pack. And then isolate your V. How much did the center of mass fall? Anyone? Yes, what? L over 6. It has fallen this far. L over 6. You plug in for I, get rid of omega, isolate your V. You're always plugging in what you got for previously, and you often get a point for plugging it in. So you had to get rid of omega with V squared over R squared. Now, we don't have R. They didn't give us R. So you need to put R in terms of L. But that part is a little tricky. You get a point for every little thing. They only give you 1 point for getting your, so this was worth 2, 4, 6 points. For any indication of conservation of energy, you got 2 points. So for writing conservation of energy, you got 2 points. For correctly calculating the change in potential energy of the rod or the work done on it with mg L over 6, you got 2 points. For putting the kinetic equal to the potential, you got a point. For getting rid of this with V squared over R squared, you got a point, even if everything else was wrong. And now we need to get rid of R squared, but you only get 1 point for the final answer, which would include the R squared. So you have to figure out what is R in terms of L. What is the radius of this rotation? And that part is a bit harder. I can cancel out my M. I'm looking for V, so I can get rid of one L. Just gonna move this up. I've got 18 over 6G. Is equal to, and then I move down.
Wouldn't that just be equal to 3G?
Yes, it would. And then I have one L left. Okay, so what's the R? Can anyone tell me?
L squared.
Okay, so it's rotating from here. We're looking for the R that's related to the omega, okay? And we're looking for this V down here. So this is the R.
So is it 2L?
Right. It's 2/3 L. This was the radius for this. We're looking for this V in this rotation. So that one was hard. So then we have V squared divided by if I move up my R squared over here, I'm going to just move it up here. I get 2/3 L quantity squared. And then I move down one L here. And then we can do some simplification here. I think you need to simplify this. 3G. We square this, we get 4/9 L squared over L, right? So one of these L's cancels. Something like this where you're isolating your V, I think you should do a little simplification. But if it goes on a long time, they only give you 1 point for the correct answer. Don't ever do a long time simplifying. It's not worth it. So I take the square root of both sides. Okay, so right now I have 12/9 or 4/3. So what I have here is 4/3 G times L. I can take the square root of both sides and get square root of 4/3 GL is equal to V. So you remember how it always comes out when you're doing conservation of energy and isolating your V for something that's rotating, it's always coming out to some square root times some constant times G. Okay, let's go to C. Now, when I gave you your card, I told you should write down certain equations that you should memorize because it really helps if you memorize that. They expect you to know it, but they don't put it on the card. So when this thing drops down, regarding its timing and its motion, do you remember what it's called with regard to physics? I could have a baseball bat dropping down. What is that? Calculate the period of oscillation as it swings. Do you remember what it's called? You have a baseball bat that drops and is swinging. You could have a club that drops and swinging. A meter stick drops and swinging. What is that called? What type of pendulum? There's two types. There's bob pendulum. What's the other one? Physical pendulum. This is a physical pendulum. So I had you write down your equation for the period of a physical pendulum and put it on your card. Did you do that? What do you have?
2 pi times square root of I over MGL.
MGD or MGH? NGL, I guess you could call it L. Okay, so good. Now that it helps to just memorize this equation because that's what you need to use here. And how would you know? So you get a point for writing your equation for the period of a physical pendulum. I kind of remember it like inertia over potential energy. So I have my equation already for period of a bob pendulum. And instead of L over G, I just remember it like inertia over potential energy, because really that is the same equation.
So what was it?
2 pi I over mg, whatever your change is, L or I have D or whatever you want to call it. 2 pi square root I over mg. You could call it D, you could call it L, you could call it H, whatever that changes in height. Okay, now, you sub in your inertia, you get a point. Now, then you have to figure out what is the distance D you're talking about. And you sub that in. That's a third point. And the correct answer is the fourth point. So usually if you had the wrong inertia, you subbed it in, you'd still get full credit. So just sub in your inertia, figure out what is your D, and then see if you can simplify that, because that one you also need to simplify, but hopefully it won't be too hard.
I'm wrong.
Me too. Always been on track.
I know here's like,
Our, part A is when we got the inertia. I think we just put that in.
yeah. Well, I'm at this point, I'm really accepting the thing that I'm not gonna pass the physics final. I don't technically need physics, so that's doable.
So I don't think you credit that bad.
I would like it, but is the video still working?
Yep.
Good.
Yeah, it took. I'm so happy. Did you get it? The distance for the oscillation is, again, what part of this is oscillating? It's this. It's the distance from the pivot to the center. It drops down. How much is this oscillating?
1/6.
L over 6.
Are they in order?
Yeah. Okay, so you plug in your inertia, ml squared over 9, then you plug in L over 6. You can cancel your m, you can cancel one L. You simplify that, just show me your answer.
Dr. Martin, I think you might be out of state.
Okay.
I punctured a hole in this thing.
What do you have, Samuel, for your simplification?
I have 2 pi times the square root of L squared over 9 over G times L 6.
That's right.
So you have 1/9 divided by 1/6, right? That's 2 pi. L squared over L just gives you 1L over G. And then 1/9 divided by 1/6 is the same thing as 6 divided by 9, which is 2/3. Okay. All right, I just passed out 2000. So we're finished with 2000. We're finished with 2004. We're going to do 2010 next, which has a nice UGU problem. So that's good practice for you. It also has, exponentials in it, so that's good too. We're going to go on break, and so if I'm struggling to get this thing going and trying again, I'm going to have emailed you the 2010. You can always just get started on number 3, 2010, which is a calculus problem.
Oh, yeah.